Hello and welcome to a CFD tutorial on how to simulate compressible supersonic flow over a rocket body. So first thing we're going to do is open up our geometry, and we're going to open up a new design modeler. And when that loads, we are going to begin importing our rocket geometries. Now, if you're taking this, if you're watching this video in Professor Allhouse's CFD class and you want to run a simulation and have it be able to write the motion history and for it to have enough data to run, you're going to need to do it on your local disk. And I'll talk a little more about that at the end. But we're going to generate our first geometry. This part's sped up to ×2 speed. So you can see it takes quite a little bit. You can make them .step files that will make them load a little faster. Oh, random error. We're going to exit that out. And when it loads, we're going to put another one in there. And the reason is we're going to use the Boolean tool in a little bit. And we do that, Ansys consumes both of the imports to make that Boolean. So we need 2 of every interior one, and it will make sense when we start Booleaning in a little bit. Booleaning in a bit. So let's skip ahead. Okay, we have all of our geometries imported here. You see we have 2 of each geometry, 2 inner rockets, 2 rotates, 2 outer rocket ones, and then 2 outer domain ones and 1 outer domain 2. Now we'll use the Boolean tool. We're going to put subtract right there, and we're going to select the innermost rocket body. There we go. Oops, I had a little bit of a mix-up right here. There we go, accept. Then we select the region that is outside of that mesh. And we're going to generate. You'll notice that we went from 7 parts to 6 parts. 2 of our parts became 1 part, so we subtracted 1 overall. And we're going to go down the list and keep doing this. So when that's finished, we'll generate our mesh, and then we will suppress our rocket body because we do not want Ansys to create a mesh there. We want it just to be empty space. And then we'll form a single part from all of our mesh regions, and this will become our fluid simulation region. So after that, we'll save the project. We'll call it rocket round edge. We'll save that, and then we will open our mesh. I'm going to wait for that to open up. This is ×2 speed. It takes a little bit. When it loads in, we see our mesh right here. We're going to insert our method for how we divide up the elements within our mesh. And we're going to make sure that the body selection tool is on, and we want quadrilateral dominant method. Now we begin inserting sizing for each of our meshes. The closer it is to the rocket body, the higher resolution we want the mesh to be. And so we're going to change also metric down there from meters to millimeters because that's the size we're working on. Saves on computational power. And then for the mesh outside of the original mesh, we're going to make that 0.5, and the outermost mesh, each element will be 1 millimeter. Then we'll generate our mesh. This part takes a bit, so we're gonna skip ahead to when it's finished. Now it's done, and we can see that the resolution of our mesh changes the closer we get to the rocket. And we notice that the mesh looks pretty good. There's not a lot of obtuse shapes or anything too crazy. But from this point, we're going to start creating our name selections. So we'll zoom into the rocket, and we'll have edge select on before we highlight the regions that form the rocket body. And we'll call that move wall. Ansys is pre-programmed, so if we prename our mesh domains, or actually prename our mesh, they will apply certain conditions to them in the setup stage of the simulation. So we call the region closest to the rocket domain 1. This is for our dynamic mesh in a little bit, and the outer region domain 2. We're done. We can set up our velocity inlet. This is where the direction of the arrow will be coming from. And then we'll select our pressure for our fields in the top and bottom. And finally, we'll select pressure outlet for the end. When that's all finished, we're just going to double check again. Our move wall, that looks good. Domain 1, the region closest to the rocket. Domain 2, the outer region, the deforming mesh. Velocity inlet, pressure far field, and the pressure outlet. So that's all set. We're going to save the project. And we will begin setting up, or we'll update our mesh, and we'll begin setting up for the simulation. We're going to make sure double precision is on for processors to make it quicker, and we will save. And when that loads up, I skipped ahead, it takes quite a little bit. We're going to press OK. We are going to zoom in on our mesh, and we're going to select a density-based solver, and it's going to be transient as our rocket is going to be moving. It will be pivoting around its center of mass. So we go into models and we turn on the energy model. This will be so we can set the air properties to an ideal gas, which will make our calculation more accurate because we will initialize from the far field using a Sutherland calculation for the viscosity properties. Let's press OK. Change, and we'll close that up. And then we'll set our boundary conditions, our inlet. We're going to try to simulate supersonic flow. So we want it to be slightly larger than 1 Mach. We'll go 1.152, which luckily for us will add up to a very nice 400 meters per second. We're going to select components for velocity specification because we are going to include a wind change at 0.0015 seconds, so we are going to select component, and we'll set that up in the dynamic mesh, which you will get to see, which is right now. So we're going to check dynamic mesh, we're going to turn on layering and remeshing. This means Ansys will remesh the outer domain. We're going to select our mixture diffusion's on, we go to layering and set ratio base to 0.2 and 0.15. That's just what works best for our simulation right here. For parameters, we're going to set default, press OK. And now, 6 degrees of freedom in the options. We're going to press setting and create a body. This will be our rocket body. In SolidWorks, we made sure that the center of mass was 1/3 of the way from the tip of the nose, as would create a stable rocket that way. We're going to select 1 degree of rotation, and we've calculated the moment of inertia beforehand, so we're going to put that in as well. Save that. And write motion history. Now this is the part where if you are doing this in Professor Allshouse's class, you will want to run this in the local drive. But if you are disconnected from the local drive for any amount of time, you will lose all of this data. So you're going to want to run it all at once. And this is where we set the events. So we're going to set 2 events. The first one will be velocity inlet, and the second one will be pressure far field. The time we want the event to occur at is 0.0015 seconds. And then we'll set some executable commands that Ansys will execute after this amount of time. So if you wanted to simulate this yourself and you want to increase the time steps or introduce a dynamic event at any time, you can adjust the time here and adjust how much the Y velocity changes to. You can also set that here. We're just going to check again to make sure. Yep, that's pressure far field. That's good. Check again. This velocity inlet. That's good. And we'll save that. And now we can set up our dynamic mesh. So the actual rocket will be we're going to make sure 6 degrees of freedom is on. Domain one. Sure that is passive, so it moves with the rocket body, with the move wall. And finally, domain 2, which is the outer mesh, will be the deforming body. We're going to go to meshing options and make sure that for parameters, we're not going to use global settings, we're going to use local settings. And the reason we do that is because we don't want the deformation scale to apply over the entire mesh, we just want it to apply to the second domain. So we're going to do that right now. Save, close. And now we'll add our reference values. We're going to make sure that the area we set for our reference values is the area that is perpendicular to the flow, which in this case would just be the rocket nose. report definitions, we're going to create drag and lift reports. You have a lot of options here to choose what type of reports you would like. But for this simulation, we just want drag and lift. Now you can create, you can print the output to console and create an output for that, so you can see the scaled residuals to see how accurate your answer is, or excuse me, the result is. So you can turn that off if you're not interested in seeing that value. And I will rename these. Actually, I don't like that it's called def 0 and 1. We're going to call that drag and lift. Very good. And in the reports, we're also going to rename this drag and lift. When that's all done, we'll actually initialize our calculation. So we're going to initialize our calculation from the pressure far field. This is because the pressure far field is simulating a stable fluid, and we want to use an ideal gas. We want to use the Sutherland calculation. So there are other methods of setting up a supersonic flow calculation. This is just one of the ways to set it up. And because of the way we set it up, we are going to compute from the pressure far field. Now we're going to work on contours. We're going to create contours that we're interested in: static pressure, x velocity, y velocity, and the Mach speed. So this is the part where you can really customize your project. Take your time, zoom in, or find the parameters that you like, and create contours for them. Now you go into calculations, solution animations. This is the part where I meant to say you can now customize a lot of what your output is going to be. I can zoom in a little bit, set active. And as you can see, I set to record after every one-time step. I'm going to change this to 10. If you have a lot of data and you have a fast computer, set it to 1 if you want that type of resolution. But for me, we're not that interested in that type of resolution, so we're going to set it to 10. And it'll also make our computation faster. So trade-offs. Now we're going to run our calculation. Or excuse me, if you want to see your playback at the end, which I will also show you, they'll show up here. But now we will get ready to run our calculation. Our time steps is based off of when we set the dynamic event to happen. In this case, it happens at 0.0015 seconds, so we'll run 3,000 iterations to capture steady state before and after the event, and we'll use 1 e to the negative 6 to give us some good convergence on the residuals. So let's calculate right now. There we go, off to the races. There the scale residuals go. I'm going to wait right now. It reports after every 10 iterations, so we're going to wait to see the first 10, make sure things look okay. There we go, our simulations have begun. We can take our hands off of the reins for now, but here it will be calculating. You see our reports for lift and drag and our scale residuals. We want these to go down, we want it to converge. So we'll be running this. Okay, it's been a little bit, and the calculation's done. So that's all good. We can now take a look at our scale residuals. We'll notice that if we check at the very end, our highest, the value of our residual that was the highest was to the negative 6. So that's okay, acceptable. We want it to be lower than that. To the negative 3 would be barely acceptable, so we did all right on that value. We can check out our contours right here. And then if we go over to playback, we'll be able to watch these animations take place. It's pretty nice, looks pretty good. I will not comment on the nature of the shockwave development. I'm still in the phase of learning about that as well, so when I know more and am more educated, I would love to come back and talk more intricacies on it. But it's not just about making really nice animations. We also want to export our data. So the rotation of our rocket, in this case, which we set before in the dynamic mesh, it's output right here. And if we want to see our drag and lift reports, they will be in the files, dp0, ff, Fluent, and here's where all the pictures of our animations are saved. But if we scroll all the way down, we'll see files for our lift and drag. So you can convert these to TXT files and use them in your MATLAB coding. And that's all we have. So I'll leave you with the Mach number. It's the prettiest one, I think. And thank you so much for watching. And you should take Professor Alhaz's class. Yeah, that's it. Take care. Bye.